Thank you, Sylvain, and thank you to all the organizers for this opportunity. So, although the meeting is on rotating and stratified flows, for the most part, I'll be talking about non-rotating and unstratified flows. Uh, the point is to give a basic introduction about hydrodynamic instabilities, and many of these instabilities and these concepts will carry through to two rotating and stratified flows. Once or twice, I will refer to rotating and stratified or stratified flows. Okay, so why do we need to study instabilities? That's the first question. Why do we need to do this at all? So the first thing is, of course, that instabilities tell us about the flow going from laminar to turbulent. And this transition is an extremely complex process. It's a process which depends on the flow we're talking about. It depends on so many other things. And in order to understand that process, we need to study instabilities in great detail. So, and the next thing is in all of these transitional or even turbulent flows, we always need information about mixing and dissipation. Remember, the second talk today was all about mixing. So, you really need all the time, quantitative measures of mixing and dissipation, and you have no way of understanding these things if you do not know about instability. So, there's many quantitative things you need for which you need to study instabilities. So here you will see a pipe. You'll see the same pipe in three situations. Here it is in laminar flow, here it is in turbulent flow, and here it is in a transitional flow. So just to give you an idea, in the laminar flow, it's always steady with time, and the velocity profile looks like a parabola. In fact, it is a parabola. So, this is what the velocity looks like, with the maximum velocity at the center line and no slip at the walls. And this I'm talking about pressure driven flow through a pipe. I'll often be talking about pressure driven flow through pipes and channels. Now, at low Reynolds number, this is what the flow looks like. At very high Reynolds number, this is what the flow looks like. So every blob of fluid goes through seemingly random activity, goes into completely arbitrary trajectories. It looks like we'll see that these are not all that arbitrary. And then there are these structures which have drawn one streamwise roll, a role which is aligned in the streamwise direction. This we'll talk about a lot tomorrow. So these roles are a very important part of turbulence and of instability. So, and they're very important part of any wall bounded flow. So we will talk about these in some detail, and we will see what we can make, how we can make sense of this seemingly random flow. The turbulent velocity profile on the mean looks like this. It looks very clean and smooth. And the beauty is that given the Reynolds number, given the pipe roughness and so on, this velocity profile is invariant. So you can come back tomorrow and do the experiment, day after tomorrow, go to another pipe. Everything, all the mean properties are invariant in turbulence, which is why we need to study turbulence. If it's going to be a completely random phenomenon, then we can't predict anything or we can't go anywhere with it. But that's not how it is. We can predict so many things about turbulence, which is why we study it. Now, in intermediate Reynolds numbers, you can get turbulent puffs in the middle of a laminar sea. So this is the kind of insight you gain from studying instabilities. These streaks that I'm talking about, these long streamwise vortices and low speed streaks, which we'll talk about, are a very important result of instability, as we will come to, and they determine so many things, including shear stress at the wall. This is one reason to study laminar turbulent transition. Another reason is plain aesthetics, right? So many times you'll see that, there are patterns created by instabilities. So here is a double diffusive pattern. We'll be talking about it in one slide later on today. And here, these are what is called aeolian sand ripples. So basically, sand on beaches forms these very beautiful patterns, which of course change from day to day, but it's just beautiful. I mean, it's a lot of fun to walk on it and keep your footprint on it. Now, this goes against everything we fundamentally learned, right? Like, we learned that everything tries to reduce its potential energy. So obviously the way for the sand to reduce its potential energy is to keep its surface flat, but almost never is the surface of sand on a beach flat. And this is because wind pushes it around and creates these ripples. And the reason that there is a length scale here, you'll notice a dominant length scale, is because the linear instability had a dominant length scale which got picked out, and it stayed as such in the nonlinear regime as well. The details might have changed, but the length scale stayed. So this is an important feature to remember about length scales. This is basically columnar basalt formation, rock formations. So how the instability happened there is a good question. So these, like, just to understand patterns, we would like to study instabilities. More than all that, so the thing is, like, why is this stability field alive after, something like 140 years where people have tried to, make sense of it? So it's alive because, okay, a lot of the questions are like being open now, and we'll talk about it tomorrow mainly, and also a bit today. Um, the main thing is, one of the main things is that it's not easy to make qualitative arguments. So we have some qualitative arguments about rotation, about stratification, which we will come to, and those qualitative arguments don't always hold. There's so many exceptions to those things, and sometimes it's impossible to guess even the sign of the stability, like whether it will stabilize or destabilize. Even that is impossible to guess, let alone the magnitude. So it's not just quantitative stuff, it's qualitative stuff we don't know. And for example, surface tension is always said to stabilize, all perturbations, because surface tension hates it when some surface area or length increases. But we know, we've recently studied a place where we've recently shown that surface tension can create a kind of funny instability in two-dimensional flow, and this should always be happening in any fluid mixture, any, let's say, oil water mixture. Such things should be happening. So lots of counterintuitive things. And one of the most important reasons that people are studying this, and why this is such an important topic in anything to do with turbulence, in particular anything to do with ball bounded turbulence, is that the signatures of these instabilities are seen in fully developed turbulence. And the question is, can these signatures alone determine turbulence, or can these signatures determine something major about turbulence? So this is the basic open question that we have here. So just to give you a motivation for that, here is a direct numerical simulation by basically Ivan Marusic's group, of direct numerical simulation of channel flow turbulence. So we'll be using this coordinate system all the time. Okay, x is the streamwise direction, that means the direction along which the flow is going, the predominant direction along which the flow is going. Y is the direction normal to the wall, and z is a direction parallel to the wall also, but in perpendicular to x. So basically it's called the spanwise direction. So streamwise, wall normal, spanwise, we'll be using these terminology. So u is the mean velocity, it's in the it's in the x direction, and it varies with y, it's a function only of y. So this is the channel flow that they've given, high pressure here, low pressure there. So flow goes this way. The Reynolds is very big, 40,000. So this is rather turbulent flow, quite turbulent flow. And what they've done is that they've taken this plane, which is slightly above the wall. Y plus is it's a small unit which measures distance from the wall. So it's, very close to the wall. There is a plane there. And on that plane, you see like what the deviations of the u velocity, that means the streamwise velocity, its deviations from the mean in that plane. So the mean is of course one number in that plane because y is fixed. So you see that there are positive and negative variations, and you see an overall stream-wise alignment. It's not as random as you think. It's not like white noise. With white noise, you would see no structure whatsoever. There is streamwise alignment, and there is some characteristic spanwise spacing. This is spanwise Z. And they've done some linear modeling with eddy viscosity and so on, and broadly they're capturing the features. So, like, you can think linear and actually go quite a distance in understanding turbulence. This is the basic message. We can't always think linear. We have to think linear when it's possible and non-linear when it's not. But there are situations when you can actually simplify the main message of turbulence. And this is an experiment of turbulent spots forming in this sea of streaks which are formed in the laminar regime. So this is a very unsteady, it is a transitional regime actually, where there are turbulent spots in a laminar sea. So again you see that streamwise alignment. That's going to be a theme of today and tomorrow, recurrent theme. Okay, so if we can't predict anything about stability, we can't say whether it's stabilizing or we can't say anything at all. And so for each flow, we have to do a different calculation, and each flow we just do the maths and get an answer. What use is all that? Fortunately, it's not that bad. There are many overriding principles which, if you understand about stability, you'll be able to guess many things about stability. And the idea of today and tomorrow is to develop a bit of intuition in that direction, and get an idea of what are the present questions in the field. I will not be listing out the present questions in the field, but that is something we can talk about later on. But it will give you an idea of what all is unknown in the field right now. So the first thing is about inflectional velocity profiles. And these points of inflection in velocity profiles are relevant to turbulence as well. So by the end of today, we should be able to appreciate why inflectional profiles are important in stability. And there are these things called critical layers. We'll define them. And it's very important to think critical layer every time you're thinking shear flow. Every time you're thinking shear flow and wave, it's important to think critical layer. So we will get a notion of this thing. Are you people seeing my cursor?
Yes, it's there.
Okay. Okay. So we'll talk a little bit about stable stratification and double diffusive instability. We'll talk about wave interactions. So this morning, Patrice had talked quite a lot about wave interactions. He called them resonance, and these are very important. So I feel like it's okay at the risk of slight repetition, but I'll be talking with a slightly different perspective to talk about wave interactions again, because you overturn many dogmas. For example, stable stratification need not remain stable when there is shear, things like that. So overturning of dogmas. So like, I didn't know what the plural of dogma is. Like, is it dogmas or dogmata? So just for looking more fancy, I put dogmata. So, okay. And we'll discuss this technique, direct adjoint looping, which is a very powerful technique in extracting, optimal things that we want, maximal things which can generate the biggest kinetic energy, things which can get you to the, turbulent side of the basin with the least effort. So many such things you can get by studying direct adjoint looping. We'll talk about two mechanisms which are important in transition to turbulence. One is the OR mechanism. It's considered less important, but in some situations it can become very important. It's a two-dimensional, very old mechanism which departs from the simple minded, linear stability studies. So this goes beyond that, and we'll see how. So then we'll also talk about a basic self-sustaining process. This is very, very important in instability as well as in turbulence. And the struggle to describe the turbulent attractor in terms of what we have learned. So we'll talk about exact coherent states, which are different from the Lagrangian coherent structures that George was talking about in the previous talk, but they're not completely, detached from them either. We'll also talk about heteroclinic orbits, with various other speakers today have been talking about. So let's start with, I'm not going in the order which I've listed there, okay? So we'll, I've changed the order partly by looking at the other talks. So the first thing we want to understand is stratification. Just get a simple minded picture of stratification. So, like, first, let's start with linear stratification. So, Anubhab many years ago made this figure, and it's a very, very useful figure. I think Anubhab is in the audience, Anubhab. So, so this is light on top, heavy at the bottom with a linear density stratification. So, d rho by dz, where z is the vertical here, is actually a constant. So, you have this thing called the Brunt-Väisälä frequency, which is some reference density, gravity, and this thing, and it's a constant in this case. So, what we can write down very easily is we can write down, like, when nothing is moving, the Navier-Stokes equations are very easy to write down in this context. Nothing is moving, nothing is rotating. So you just have a balance between fluid acceleration and the density, the buoyancy term. So when you do that balance, you just see a second order differential equation, and it's very, very easy to solve the second order differential equation. And for a certain, like, whenever n is a real number, you will see that it will just do simple oscillations. So if I take a blob of fluid here, displace it by delta z, then it will keep going up and down with a certain frequency, the Brunt-Väisälä frequency. It will keep going up and down forever and ever and ever, and it will create, it will just create periodic motion. Now, suppose instead of one blob, I had a wave, like I had an entire wave which I displaced. So, like, I take one line and I displace it in the form of a wave. So, you will see that similar things apply there as well. So, suppose I make a wave like this, I've lifted the heavy portion up and I've pulled the light portion down by making a wave here. So when the heavy portion is up and the light portion is down, what will happen is there'll be a baroclinic torque creation. Heavy always likes to come down and light always tries to go up. So you'll get this baroclinic torque creation which will stabilize this. So that is basically the moral. Of course, with viscosity, this oscillation won't go on forever. It will come back to static. So it'll be totally stabilized. Whereas in the unstable stratification, where heavy is on top and light is below, you see the opposite. And here I've just shown a step change in density where you see the Rayleigh-Taylor instability, and this time this quantity will be imaginary, and so you'll have a growth rate. So you can solve the second order equation to see that there's exponential growth, and baroclinic torque can be seen to go in the wrong direction. So it will, increase the instability rather than suppress it. Okay, so double diffusive convection is an interesting, departure from this. So here you have what you think of as stable stratification. We decided in the previous discussion that light above and heavy below is always stable. And here you have a situation where it's actually light above and heavy below. But the light is made out of two quantities, heat and salt. So you know that heat and salt are important in ocean. So this kind of viscous fingering, I'm sorry, double diffusive fingering happens a lot in oceans as well. And this was the model experiment which somebody has done in the lab to demonstrate that. She's getting beautiful fingering. I would encourage you to go to her site and watch this movie. And she's even told us how to set it up easily at home. So, although the density is overall stable, you have heat which is stabilizing and salt which is destabilizing. So, you have these two components who are acting opposite to each other, but the average is stabilizing. Now, what happens is that suppose you imagine a blob of green fluid and you bring it down here to the blue region. Then what can happen is, suppose it was warm and salty above and cool and fresh below. So what will happen is heat and salt have vastly different um, diffusivities. So this blob will come here. It was hot and salty, but soon it will share the heat with the others and it will become cold, but it won't share the salt because it will share the salt way more slowly. So because of that, it's become cold and salty, and cold and salty is heavier than its neighbors. So that makes it go down more, and then this going down will become exponentially faster and faster because it is giving heat fast and retaining salt. So this is the basic idea behind one kind of double diffusive convection. You can do the opposite and then also you'll get an instability, and you can read up about it from Turner's book or somewhere and work it out for yourself. It's a fun thing. Okay, so what is our notion of stability? From the previous two examples, we've seen that our notion of stability is just, what a child will learn in school about stability. It's exactly that notion. So, like if you take a valley and you've got a ball here, you perturb the ball, it will come back to where it was. And this is stable, whereas, a ball on top of a hill is unstable. So, a valley is stable and a hill is unstable. And in flow, we have again, we have the same concept, but we can't think in terms of valleys and hills because it's not always potential flow. It's not things going down a potential. Like sometimes you have vorticity, which is the leader. So this notion of hill and valley is good to fix our thoughts, but it's not an exact analogy. This is very important to keep in mind. So when we keep that in mind, we're still, cheating and using that analogy just to get our thoughts straight. So here is, let's say, the Reynolds number. It's a favorite, parameter, non-dimensional number, which which changes the way a flow is, and everybody here knows it. So as the Reynolds number increases, let's say there's a typical flow, like a boundary layer flow or channel flow. At low Reynolds, the laminar flow is extremely stable. It becomes less and less stable. So the hill becomes shallower till it becomes a straight line at some, critical Reynolds number. And this we call a bifurcation, where the behavior is going qualitatively different as you change the Reynolds further. And beyond this, the laminar state is more and more unstable. So this is a simple picture of the first simple bifurcation you can think of. Meanwhile, another state which was very unstable became flat, neutrally stable at the same bifurcation point, and it becomes stable now. So, like at this Reynolds number, you can have another state which is supported. For example, it could be periodic, it may not be periodic, it could be some traveling wave solution or very complicated periodic solution. There could be a variety of solutions which are not turbulent but not steady laminar. So these solutions can, live in some Reynolds number range, and then they can become again unstable, and so on. And then finally, you could have turbulence, which could not be sustained till now, and now it could be sustained. This is a very simplified picture of this bifurcation stuff. In real life, laminar and turbulent states can both be attracting, and subcritical bifurcations can be happening, and we will be coming to that in a couple of slides. So this is just a simple minded picture. So let's talk about a few standard bifurcations, and it could be any parameter, but I've put Reynolds here to fix our thoughts. And this is an amplitude of the perturbation. So like the saddle node bifurcation is one where suddenly below this Reynolds number there was no solution of this particular kind, and at a particular Reynolds number you get one unstable solution and one stable solution. Dashed lines are always unstable and thick lines are always stable. So like you get this, a kind of unstable and a stable manifold appearing out of nowhere, and that is called a saddle node bifurcation. Supercritical pitchfork, this solution was stable, the amplitude equal to 0. Let's call it laminar because we're measuring amplitudes as deviations from the laminar state. This was stable, and then that became unstable after a certain Reynolds, and two other stable branches appeared at this place. So that's called a supercritical pitchfork. A supercritical Hopf bifurcation happens a lot in boundary layers on aircraft and stuff like that, where you go from a laminar steady state to a periodic state. It's not turbulent. Steady state goes unstable, stationary state goes unstable, and you get a periodic oscillation which becomes stable. And as the Reynolds becomes bigger and bigger, you can get bigger and bigger oscillation. So in a boundary layer, this is actually not quite correct because these things are, changing with the streamwise distance. But if you pretend that the boundary layer is locally parallel, you could think of it as some supercritical Hopf bifurcations where you are going to need some nonlinearity to stabilize it to get into a periodic cycle. Okay, so we already spoke about this supercritical Hopf bifurcation as a standard thing that happens in boundary layers at extremely low disturbance levels. Subcritical things happen at higher disturbance levels, but we're not talking about that. And here, the first instability, that is this thing, occurs around 200, a Reynolds of 200, and turbulence occurs at a Reynolds of 1000 based on the momentum thickness, theta. So this is what happens in boundary layers. So between 200 and 1000, a lot of other processes happen. So in a boundary layer, as you go downstream, the Reynolds keeps increasing. So all these processes are there in one particular snapshot of the boundary layer. And then there is subcritical transition. For example, in a channel, so this channel example will come to repeatedly. The Reynolds critical. So here you have the laminar state. You go on the laminar state. It's called the lower branch solution. You come to this place which is RE critical, and then the laminar state goes unstable. However, most of the time in an experiment, you would have gone to turbulence at a much lower Reynolds number. You would not be sitting laminar till this place. It takes a lot of effort to keep the channel laminar till that place. And like very few people have been able to do clean experiments where they could actually show the critical Reynolds number taking place. There is another Reynolds number called the energy critical Reynolds number, below which you can show that all perturbations decay. Every perturbation will decay, and that Reynolds is very low, it's just 49. So, like, it's irrelevant to most of the things we're talking about now. But theoretically, nothing can ever grow below 49. Now, at in between Reynolds numbers, so like what happens is particular kinds of instabilities can show up. So, like at depending on the amplitude you start with, depending on many other things in the channel, its size, its span to height ratio, so many things come in. So different kinds of instabilities can come in the form of a pitchfork bifurcation that we so in the form of a saddle node bifurcation. So this very thing is exactly a saddle node which came out of nowhere that we talked about last time. So typically these solutions which are far away from laminar may or may not be turbulent are called upper branch solutions. Any questions so far?
No questions so far, but if someone has a question, do not hesitate to.
Okay, I'll keep going.
Yes.
So now
So there's a question.
Okay.
There's a question. What does the Reynolds CR depend on?
Okay, what does the critical Reynolds number depend on? It depends on the flow geometry primarily and the flow setup. So in a straight channel, that number is always 5772. For a boundary layer under low free stream turbulence, that number is always close to 200. So, but if you change it slightly, you make it divergent or convergent, it will be very different. For a jet, for example, it's 5 or 10 or something like that. So it depends primarily on the geometry, the boundary conditions, and the way the flow is. Is it pressure driven? Is it flowing due to a boundary movement? Things like that. Okay, so here is the energy critical Reynolds number below which everything decays. Here is the critical Reynolds number, above which we can get exponential growth of instabilities, like we saw that exponential growth in the Rayleigh-Taylor system. And here I've now started defining the Reynolds number. For the channel flow, it's going to be the channel half width. For the boundary layer, it can be any typical, size, height of the boundary layer, and some typical velocity, for example, the centerline velocity, divided by the kinematic viscosity. So it's a ratio of inertial to viscous forces. So in flows where subcritical transition to turbulence happens, you often see these streamwise streaks. Like in a channel flow. In flows where supercritical transition happens, like in a boundary layer, you often see spanwise structures. So you see these perpendicular kind of behavior in these two situations. So these are called Tolmin-Schlichting waves in a boundary layer. And actually, Squire in 1933, like 100 years ago, could already show that this two-dimensional perturbations, that means span-wise independent ones, would be the most unstable in this regime. Like, when they had no power to solve these equations properly, they could already come up with so much knowledge about this. And he had extended that for stratified flows in 1955, again before real solutions were available. Okay, so how do we go about setting up the stability problem? So we start with Navier-Stokes and continuity, and here is the Navier-Stokes equation, which I don't have to explain to you, but in case there's somebody, this is u dot grad u is the inertia term, pressure gradient, viscous term, and acceleration. Now, the subscript taught is for the total flow, and del dot u equal to 0 means the flow is incompressible. Today we'll talk only about incompressible flows. So here's the coordinate system to remind you. And we are talking about simple shear flows. So we're going to take just the simplest possible shear, where you have like u varying in a direction y, and u is all in one direction. It's all in the streamwise direction, it's varying in that direction. That is the mean flow. And then it's perturbed by this perturbation, which could be a function of x, y, z, and t. But by definition, I've made the mean of the perturbation 0. So all the mean part is collected here and all the perturbation part is collected here. Now this perturbation, I can Fourier transform. So like in this channel, we see that nothing changes in the x direction on the mean. Nothing changes in the z direction on the mean. So let me Fourier transform in those two directions with d alpha, d beta. I might have left out some 2 pi or some factors there. I'm sorry about that. Yeah, so you can write it with, you can split it into its Fourier components of wave number alpha and beta in the x and z directions respectively. And in time also we can Fourier transform, and for some reasons of downstream propagation and so on, a negative sign is chosen for that. Typically it's more a convention. And in the y direction we could Fourier transform, but we're not going to gain anything from it, so we're going to keep it as a function of y. We're going to take this partial differential equation and convert it to an ODE in y by Fourier transforming in all the other things and making them all algebraic. So like first we linearize this. So what we do is we take the u hat and we say u hat is so very small that powers of u hat can be neglected. So this becomes now a linear equation with mean u multiplying perturbation u in this term. So then do that, and then once it's linear, I can just solve for one Fourier mode, because all Fourier modes sum up. So I don't have to solve for all the Fourier modes and keep integrating. So I can just look for instability in any mode. And if I find instability in one mode, I'll know that that mode grows. So I can just choose one wave number set alpha and beta, and I can look for the omega. So basically the game is to find omega, the frequency of the disturbance, this thing, as a function of the spatial wave numbers, as a function of the mean flow, which I know as a function of y, and as of the Reynolds number. So if you stare at this, how the u hat is written for one mode, and here I've split the frequency into the real and imaginary part. The real part is just a plain wave oscillation, nothing else happens. The imaginary part, omega I, contains the growth rate. So clearly, if omega I is greater than 0, u is going to increase exponentially and everything is going to be unstable. So in our game, we are looking for omega and we are primarily looking for omega I. So when you do this exercise and plug it back into the Navier-Stokes equation and get the linear stability equation, you get this thing called the dispersion. I mean, basically finding omega in terms of alpha and beta is the dispersion relation. And this is a very famous equation called the Orr-Sommerfeld equation. It was derived by Orr and Sommerfeld in 1907 and 1908. So Sommerfeld had something to do with Heisenberg. I leave that as homework for you all. So now, every time you read about this in a book or a paper, they very often they say, we now arrive at the celebrated Orr-Sommerfeld equation. We now arrive at the celebrated Orr-Sommerfeld equation. So the adjective celebrated is often given in front of Orr-Sommerfeld. It's a very, very important equation in fluid dynamics. So since they said it's celebrated in past tense, I thought why not celebrate it in present tense. So I put some celebration for it. So now, in this, the k is just alpha square plus beta square square root. And this quantity c is just omega by alpha. It's the phase speed of the perturbation. So like having put that, and you know what v is, it's the normal, wall normal perturbation. And these primes denote differentiation with respect to y, which I've also called as d4 in this thing. So I just wrote it in this form so that I can discretize this and write it in matrix form. So what I'll do is I'll take the channel, and from this wall to that wall, I'll put little delta y dabbas, boxes of delta y, and then in each box I'll have a v. In the jth box I'll have the velocity j, uv and w of j, where I need only v for this equation. And then I will discretize all these quantities and put them in a big matrix which goes from this wall to that wall, and that matrix is called A, and B will now be a vector containing n entries, n vj entries. And then I've taken this C to the other side of the equation to write it in the form of an eigenvalue problem. So this is a generalized eigenvalue problem. I know A, I know B, and I don't know V and C is the eigenvalues and V are the eigenvectors. So I can solve for this by any generalized eigenvalue method. So this is how we solve the Orr-Sommerfeld, and before we do that, we have to plug in the right boundary conditions. And now in 3 dimensions, we have also the square equation. So I started with 4 things. Remember U, V, W, and P. I can shrink it to 2 by eliminating pressure and eliminating all the other things, clubbing all the other things in terms of wall normal vorticity eta. So vorticity in this direction and velocity in this direction. And now I get the Orr-Sommerfeld operator, which is just this guy. And then the square operator, which I've not written down, and I get an off-diagonal term. So these are actually matrices, but there's a matrix which is sitting in the off-diagonal, which is only a function of beta, the span-wise wave number. So if the span-wise wave number was 0, this won't come. So this is an important thing to remember. There is an off-diagonal little matrix based on the span-wise wave number. So this is finally the equation that we'll solve if we want to solve for eta as well. Of course, we could solve for V first and then we could solve for eta. Eta doesn't feature in V. So in order to find out about instability, we don't have to solve the second equation. Okay, so how can we simplify this, and how did people go about understanding things about it long ago, which are still so relevant for us today? So I think I'm going very slow. Okay, I'll try to speed up. So the Orr-Sommerfeld equation looks like this. Now in 2D, that means like I'm throwing away beta, and in the inviscid limit, this will reduce to the Rayleigh equation, which looks like this. So basically, I've thrown away everything on the right-hand side, and I've written V in terms of the stream function, but it doesn't change anything. Now with background rotation in the geostrophy and hydrostatic limit, You can actually include rotation also in this, so it makes life easy. We can prove one theorem which holds for both, so I've included that. So you have, suppose you're sitting on a spinning table or a spinning earth, and the rotation rate is omega. Then if I define this quantity, I linearize about a local omega, and I linearize in y, where y is the longitudinal direction. I can include a beta 0, this quantity, in this Rayleigh equation, and nothing else changes about the Rayleigh equation. Now I take this equation, simple exercise, pre-multiply by complex conjugate, it's now a row vector, and you integrate from one wall to the other. I've non-dimensionalized it by the half width, so it's -1 to 1. Integrate it from one wall to another, or any one end of the flow to another end of the flow. And then pull out its imaginary part. The imaginary part looks like this, where, remember, C is omega by alpha. And remember, we're looking for the sign of omega I, which is the same as the sign of C, imaginary part of C, because alpha is real. So like this quantity is pakka 0 for an inviscid flow in the 2D limit. If this is 0, how can it be 0? So the one way is that Ci is 0. That means you get no instability. That's one way to make this quantity 0. If Ci is 0, there's no instability, and this is anyway 0. If you want an instability, then this integral has to go to 0. How will this integral go to 0? This quantity is always positive. So this quantity has to change sign somewhere in the flow. It has to go negative somewhere in the flow, and otherwise you will not be able to satisfy this. So if this quantity changes sign somewhere in the flow such that this integral can go to 0, then you can get an instability. So, and let's now drop beta 0. Let's look at u double prime, a point of inflection. So like if this changes sign, it should go through a 0 somewhere. And if it goes through a 0 somewhere, like basically if u double prime is 0, u prime is a maximum. So that's a point of inflection. That is a necessary condition for instability. And a further condition was derived by Fjordhoff. This is the Rayleigh condition. Further condition was derived by Fjordhoff, which says it should be a vorticity maximum. The basic point is that, profiles which look like this are stabilizing in the inviscid limit. They will not have inflectional points. Profiles which look like this are destabilizing. Any wiggly profile which goes, sinusoidal is by definition u double prime 0 again and again, and it's destabilizing. So this has been used in many engineering applications. There's another important theorem called the Howard semicircle theorem, and this is going to tell us about critical layers. I mean, we're going to talk about critical layers, and this thing is going to be very important for us. Basically, again, start from the Rayleigh equation and rename phi in terms of another variable a, and you'll get this very simple quantity, which is that the real part of the phase speed c should be somewhere between the minimum and maximum u in the flow. So in the channel, you have u max here and you have 0 here. So the phase speed c has to be somewhere between this value and this value. So there has to be one layer in this flow where this capital U is equal to c. That means this term goes to 0. That's called the critical point, and there's a thin layer around it called the critical layer. This is going to exist. That's what the Howard semicircle theorem basically tells. It's called a semicircle theorem because there's a limit on Ci as well, which I'm not calculating, and that goes as a semicircle. So now, remember we just said, Reynolds is very large, so I'm throwing away this right-hand side and I'm working in the inviscid limit. The question is, can we always do this if the Reynolds is much, much, much greater than 1? So suppose the Reynolds is 1 million or 10 million. Am I justified in doing this? That's the question that we need to ask. So, okay, so then, so can we always do this if the Reynolds is very large? So your instinct will be to say that if the Reynolds is 10 to the power 10 or something, like in Jupiter, I can throw this away. But you actually cannot throw this away. If you stare at it for 1 second, you'll realize this at once. It's because the fourth derivative, that means the highest derivative, is multiplied by 1 over Reynolds number, and on this side you have only a second derivative. So remember, I had these 4 boundary conditions I needed to satisfy. So obviously I can't satisfy all 4 boundary conditions if I throw away the 4th derivative. I'll get something with 2 constants, so I can only satisfy 2 boundary conditions. So I know I'm in trouble already, close to the wall. So in the wall is where I have to satisfy these boundary conditions. So there is a wall layer where I'm in trouble if I throw away this, however large this is. So this is giving me an idea that viscous effects are a singular perturbation. What's a singular perturbation? Let's do a simple example. So forget about the flow for this slide. I've taken x dot plus 1 is 0, which I can solve to x equal to minus t plus c. Now if I perturb it slightly, very slightly with an epsilon, but I've increased the order of the differential equation. Of course, this is a simple differential equation, I can solve it fully. But if I couldn't, what would I do? And how would I account for this? I know that at one boundary, in one of my boundary conditions, this term is going to become extremely important. So what I do is first I get an outer solution where I don't consider this thing, and I solve for that. And then I write a boundary layer equation for the inner solution. That means where this thing is important. For that, I recognize that the only way this term can become important when epsilon is very, very, very small is if the second derivative will grow and grow and grow as epsilon becomes smaller. And then that term becomes order 1. So I know that I'm talking about a time scale which is very, very short, where lots of things are happening. So in order to account for that, I rename it by giving another time scale of order 1 and multiplying it by a small number delta to give my real time. And then I write my equation in that variable. Immediately I see that this term is very important and this term is less important. This term is less important, and I can get an expression for delta and get a reduced boundary layer equation. So this equation is the inner layer equation which I can solve. So I do the exact same thing for the Orthomophild equation, except that viscosity is important in 2 layers now. So near the wall, u is practically 0, so I can throw away that term, and I rename my y in terms of wall variables, and I'll get that the lowest order equation is just this, from which I get that the length scale over which the viscous effects are important near the wall, that length scale scales at Reynolds to the minus half. In non-dimensional terms, it scales as delta W should be Reynolds to the minus half. Sorry, typo. Here also it's a typo. There's no square in these things. So in the critical layer where U is equal to C, that's another place where viscosity is most important, and it plays like very great havoc over there. So what is happening in the critical layer? So in that critical layer, I can write the velocity as a Taylor expansion on C, and I do the same exercise. Within a few lines of algebra, you will get that there is a layer which is Reynolds to the minus 1/3 thick, which becomes where viscosity becomes important. This is a very famous scaling, minus 1/3 scaling. It goes back to C.C. Lin in 1946. It's very relevant in turbulence and everything today. So that's the critical layer. So here is just a recent example of how people look for critical layers and how its importance is increasing. So you remember I told you there are these streamwise streaks happening a lot in turbulence. So here is a model flow where they made these streamwise rollers, streamwise vortices, and these vortices, they pull up low velocity fluid from the wall and push down high velocity fluid from the from a little distance away from the wall. So you're getting low velocity streamwise flow here and high velocity streamwise flow here. And these rollers or these vortices are creating streamwise streaks. And if you take the Fourier component of this streak is now a very messy object, but they took the most powerful Fourier mode, which is not changing in time. The omega real is 0 in time. And when they did that, they found that the majority of the flow is concentrated at the critical layer. It's not in a straight line. You can actually calculate that U equal to C, U equal to C layer here, and that is not a straight line. And wherever the critical layer is, that's where the main flow is. So a lot of energy is being produced at the critical layer. So the production of kinetic energy is a very viscous thing which happens a lot in the critical layer. Okay, so Kelvin-Helmholtz instability, everybody knows, so I'll go through it quickly. Basically, like it's a jump, any jump in velocity is invisibly unstable. That's what the Kelvin-Helmholtz instability tells you. There's always a CI if you look at this. So then, like, and the model for that can be easily understood, but I'll skip it in the interest of time. So here is what a simple thing called a Rosby wave. It's not Patrice's Rosby waves that he was talking about in the morning. More than one thing goes by the same name. So here we have a flow like this, which is constant velocity here and shearing here. So like you're just going from shear to no shear. That's all in this flow. And this nothing, there's no instability in this flow, it's neutrally stable. And you can see that very well by writing down the dispersion relation and even by staring at it. So if you perturb the interface, this dashed line, if I make it like this, then what will happen is here the vorticity is 0 and here the vorticity is a number. So relative, here the negative number. So relative to the surroundings, this one will have negative, positive vorticity. And any positive vorticity introduces a downward flow here and upward flow there. Negative vorticity, downward flow here and upward flow there. So you'll be inducing these downward and upward flows, which will just take this interface will be pulled down in these parts. That's all is going to happen. In other words, there's a wave propagating in this direction. So these particles may be going up and down, but the minima of these waves will be, minima and maxima will be propagating in that direction. So you just have a neutrally stable wave. Now you put two of those neutrally stable waves together, as Patrice was showing in the morning. You put them together and you now get an instability. This guy on his own was stable, this guy on its own was stable. And now when you put them together, they can actually phase lock. They in fact actually phase lock. They choose a phase, special phase between them. And in this phase, when this interface is coming down, it pushes this one a little more. And so on. It creates a velocity like that. So they can, it's like two flags flapping in the wind, which can, flap faster and faster because they push each other. So this phase difference determines the instability, and when that phase difference becomes unfavorable, you get stable. So you can write down this thing, which is basically the Kelvin-Helmholtz instability at low wave numbers, that means long waves, and it gets cut off at high wave numbers. So this is basically, if this thickness B goes to 0, you'll shrink back to Kelvin-Helmholtz instability. And viscosity is a thing which modifies these phases, as we'll come to. So just because this Holmboe instability and these things have been discussed a lot, here is another case which Harish computed. I think nobody computed it before him, but I'm not sure. You basically have a stable density stratification and this Rosby wave, which is stable on its own. It's just neutrally stable on its own. Put them both together at a distance d, and you can get instability of this form, where gamma is the shear rate here. So you can get instability out of the wave here interacting with the wave there, which you can call as a wave interaction or a resonance. So you're creating an instability where there was none out of two stable things. Okay, so like viscosity is the creator and viscosity is the destroyer in these situations, in many of these situations. In situations where you don't have an inflection point, you have actually no means of getting an instability by the inviscid mechanism. But viscosity can do that. So like if I write the kinetic energy equation, I can club it like this. The Orthomophild equation can be written in terms of a kinetic energy equation where the net change in the total kinetic energy in the flow can be written as production minus dissipation. This quantity is always positive, so dissipation is always positive, namely kinetic energy always goes down due to dissipation because of this minus sign. And this quantity can be positive or negative. It's easy for me to see that suppose I have u and v, which are two sinusoids, just a sin omega t and b cos omega t. the average is always going to be zero. If I average it over the entire domain over all time, I'm only going to get zero. I'll never get a production of disturbance kinetic energy. So, whereas viscosity introduces interesting phases between them and interesting phases between them as a function of y. So, this kind of wave interaction happens continuously along all the layers. The two waves we drew, that kind of thing happens continuously in every layer. And because of that, like, instability can happen. So viscosity can produce an instability out of nowhere. And incidentally, most of this production of kinetic energy is in the critical layer. In the previous example, you saw that most of the fast speed flow was in, I mean, big perturbation was in the critical layer. Also, it's where the thing is produced, and it could be transported elsewhere. But it's very important to note that where viscosity is important, that's where you get production of disturbance kinetic energy when you do not have an inflection point. Even when you have an inflection point, this plays an important role, but we won't go into that. So Paul Linden also showed some C equal to U type cases. So that's why, like, a pressure driven flow through a channel, this is 1 minus y square profile. So U double prime is -2 everywhere. It never satisfies the Rayleigh criterion, but it's linearly unstable above some Reynolds number, where the critical layer can start winning over other things. In the Blasius boundary layer, same difference. There's a critical layer, and U double prime is not constant, but it's negative everywhere, but you get this linear instability. So when we talk about the inflection point theorem, which says instability, a necessary condition for instability is an inflection point. No inflection point and you got instability because it's a viscous flow. The theorem doesn't hold in viscous flow, so handle it with care. But in spite of this warning, we use it all the time, because anytime you see an inflectional profile and compare it to a non-inflectional one, you'll see that the inflectional one is more unstable. So you can easily make guesses about instability or the direction in which instability is going from the direction whether it's going towards inflectional or not. The Howard semicircle theorem works a lot of the time, not all the time, I should say a lot of the time. So we always have critical layers, which makes life interesting. Okay, so this is just a counter example for a rotating channel. I'm going to just mention about it. So, like, what happens here is that in the morning you heard Patrice explain to you how, the Taylor-Prudman theorem basically makes every perturbation two-dimensional. It makes variations in the rotate. Suppose the rotation axis is this, it makes variations along the rotation axis zero. So, like, all variations are in the plane, and Coriolis, like, has a natural tendency to act as a restoring force. So whatever perturbations you put, especially if you're trying 3D perturbations, they're going to be killed off immediately and you're going to stabilize. So a common dogma about rotation is that it stabilizes. Well, here is a case where it's doing the opposite for at least some part. So this was a paper written by Jose and some of us some years ago. I think Jose is in the audience. So, like, here, like, you can think of a pressure-driven channel sitting on a rotating table. I mean, all channels are sitting on the rotating Earth, but we don't feel that rotation so much because that Rosby number is too large. But in this case, you can feel it if you're sitting on a rotating table. So that is the geometry we're considering, and at high Rosby numbers, the stabilization does come to play. So, like, here is the Reynolds number of instability, and it basically shoots to infinity for high Rosby numbers. So at very, very high Rosby numbers, you always get stable flow. But remember, for no rotation it was 5772. It's come down by 2 orders of magnitude. You're getting exponential growth for small rotation at a very low Reynolds number. So rotation is actually destabilize this system. Besides which, it can it can aid or hurt transient growth, and below this Reynolds there's a monotonic decay which doesn't change too much with the rotation number. So any shear flow can show subcritical instability and transition. And this is a point I want to make, and we will talk about it in much greater detail tomorrow, but it's important to make. So, what happens is in a Poisson flow, we've seen that the critical Reynolds is 5772, but we've also seen that very rarely can you reach 5772 while being laminar. Unless you're doing a very careful experiment, you can't even see it. You'll see turbulence at a Reynolds of the order of 1500, depending on the disturbances in your flow and depending on particular situation in your flow. Similarly, a pipe. So this is called a Poisson flow and this is called a Hagen-Poisson flow. Both are parabolic profiles, but one is in an axisymmetric geometry, and that changes a lot. It changes a lot because in an axisymmetric geometry, if you do if you write Orthomophild in an axisymmetric geometry, you'll never get any instability. The omega I will always be negative for any Reynolds number. So it's always linearly stable unless there's some instability lurking somewhere that nobody has found till today. So it's basically linearly stable at any Reynolds number. But all of us who've been through even some elementary fluid mech course have learned that pipe flow is turbulent at 2000. So I will not go into that debate about whether it's exactly 2000 or 1500, but all we need to know is that turbulence happens much below RE critical. So here is RE critical and here is turbulence. So that's what is happening. And so it's, some complicated set of subcritical bifurcations happening. And that's why it's important to study subcritical instability. Even in turbulence, subcritical instabilities are constantly happening. So it's extremely important to study them. So I will do this particular one and stop here. Or do you want me I can do this tomorrow also if you like. Hello?
Hello, maybe you can, I don't know, maybe you can continue what you have
Okay, I can
planned.
stop this and take questions. If there's time at the end, I'll do this.
I don't know, maybe if there is some questions now, people can ask a question now. Otherwise, you can continue this. I don't think there is any question for the moment.
Okay, so I'll continue this. Okay, so now in this subcritical situation, you get both laminar and turbulent can be attractors. So here we're talking about sitting between this Reynolds number and this Reynolds number. And you see that here is one attractor and here is another attractor. So both of them are stable solutions, which we call as attractors. There's something, unstable between them. And that's the scenario we are considering. So it's of course a complicated, very very high dimensional system. So in that very high dimensional system there is a high dimensional basin boundary, which I've shown by this line, and anything that starts on that side of the basin boundary will go towards turbulence. Anything that starts on this side of the basin boundary will go towards laminar. And sometimes this basin boundary can come rather close to the laminar attractor. And one important game which is now being played, which is important for many situations, is to find the minimal seed. Namely, if I plot disturbance kinetic energy, circles of equal disturbance kinetic energy away from the laminar, then what is the minimum perturbation energy I need to put to be on the other side of the basin boundary? So that I go towards turbulence. So, what is the minimum thing I need to do to the laminar flow? And what is the shape of that perturbation? What is the description of that perturbation? What is the smallest thing I need to do to go in towards that? And now, what happens is there is this basin boundary, which basically says that if you did the FTLE that George Haller was talking about, you will see a maximum in this FTLE. So this you can think of as a ridge. It's a ridge in some very high dimensional space. And anything starting on this side will fall here, anything starting on that side will fall there. So by an FTLE, I can very easily get this basin boundary. So one way to get the basin boundary would be to do an FTLE, which is finite time Lyapunov exponent. Okay, now on this basin boundary, what will happen is there will be one or more saddle points. There'll be one or more saddle points. This is the way turbulence works. Okay, so now any nonlinear dynamical system between two attractors, there'll be some unstable manifold. These are basic theorems in nonlinear dynamics. So there could be one or more saddle points. So let's say there's one saddle point. This is called the edge state or the edge of chaos. It's called the edge state. So in this edge state, so what happens is, suppose I start just on the other side of the minimal seed. How will I go towards turbulence? I'm on this stable manifold part of the saddle. So there's something taking me along this. So like this blue line I've drawn a bit far away, but it's actually very close to this red line. So it will keep shadowing this stable manifold for a very long time until it reaches this place, and then it will race along the unstable manifold towards turbulence. So similar thing will happen if I start here somewhere on the laminar side. For a very long time, it will just go along the basin boundary, and then it will race away exponentially fast. So this saddle point behavior will do that. So the thing is that this ridge is very important. It determines who's on which side. It also determines the time scale on which flows are approaching the turbulent attractor or the laminar attractor. And one more thing is that we know that at very, very low Reynolds number, there is no turbulent attractor. This one I'll talk more about tomorrow. For very low Reynolds, there is no turbulent attractor. So we are sitting on this regime. And for very, very high Reynolds numbers, this model may or may not be correct. There may be still a small attractor, like it may always be subcritical. In other words, this thing may or may not go towards RE critical. For example, in pipe flow, the RE critical is infinite. So you could have, this thing going on forever and ever and ever. So in other words, in pipe flow, you could have, in all flows, typically you're going to have this basin boundary shrinking the laminar basin of attraction. The laminar basin of attraction is going to shrink as you increase the Reynolds, and the turbulent basin of attraction is going to increase a lot. Whereas in the pipe flow, there may always be a small region, like very close to the laminar attractor, where there'll still be a basin of attraction. It will never go unstable. So this is probably a good place to stop today.
Is there any question? We have time for questions, so do not.
Okay, so I guess there are no questions.